So the next one we got to look at is the axis of rotation. Okay, so in the early solar system, there was actually a collision between the Earth as it was slowly developing and another sort of planet or planetoid. And the result of that collision was actually the moon. Like all the debris that got thrown off, it coalesced into the moon, and it's one of the largest moons that we know of. But what also results in that is instead of our axis of rotation, so the way that the Earth spins around its axis, instead of it being vertical like this, it was actually knocked at an angle. And this means that when the sun's the solar insolation from the sun, so here's the sun in the distance, when it strikes different parts of the surface at different times of the year, it gets spread out to more or less of a degree. So in the northern hemisphere, in the summer, the northern hemisphere is tilted towards the sun. Okay, and that solar insolation is spread over a set distance. Now, the Earth orbits around the sun until it's on the opposite side 6 months later. And then we find that the tilt of the Earth's axis in relation to the sun has actually stayed the same. So now the northern hemisphere, so the northern side of the Earth, is now tilted away from the sun. And you can see that the solar insolation has to get spread over a much bigger area. And this provides us our seasons. So seasons are produced by the axis of rotation being tilted. Okay, and how spread out the insolation is. The amount of solar insolation doesn't change, it's constant from the sun, but how spread out it is over the planet does change depending on the season, where the Earth is in relation to its orbit around the sun. The next one we have to look at is the speed of rotation. Okay, so not only does our planet orbit around the sun, so here's the Earth again, and here's its tilted axis of rotation, but our planet also rotates around the axis of rotation. Now this is really important because it means that not one part of the planet is ever exposed to the sun for longer than any other part of the planet. Okay, so the solar insolation is sort of evenly distributed by its rotation. Okay, so the rotation is a 24-hour rotation. Okay, and this prevents extremes of temperature. Okay, if it you do find that there are planets, exoplanets that we discovered where they are locked. So one side of the planet is always facing the sun or the star that it rotates around. and this means that that one side gets incredibly hot and the other side is always exposed to space and always in shade from the sun and gets incredibly cold. And we don't think that allows for liquid water to be present, meaning it's much less likely that life can develop in these sort of planets. And then our last feature of the Earth that makes it possible for life to evolve and develop, in that early Earth, all that heat caused there to be a molten core, and we still have a molten center to, or part of the center of our planet. Okay, so we have the outer crust here, which we are familiar with. It's like the solid outer layer, and it's relatively thin, and it's got made out of tectonic plates that move around, and those moving tectonic plates, this is the crust made up of tectonic plates, they move around on the mantle, which is like a sort of moving plasticky liquid superheated layer of rock. Okay, and that's quite a big part of it. So that is our mantle. And within that, you have the core, which is divided into an outer core, which is actually moving around. Okay, and then inside of that you have our inner core, which is so heavily compressed that it can't really move and it's practically solid. But this outer core, we think that there are like convection, like currents within it that move, and because it's made up of high and iron, this moving outer core, so they sort of swirl around, that's my inner core again, because it's high in iron, it's got high iron content, it's moving, and this means that it generates a magnetic field. Right, now this is really important because if I just shift this over a little bit, so I've got a bit of space. Not quite right. Let's try again. What we find is the sun. So here's the sun over here. It releases charged particles. Okay, and these charged particles are moving at incredible speeds away from the sun. And if they reach the Earth's surface, they would cause any living thing to suffer from genetic damage to its DNA and cause genetic mutations and death. But this moving iron-rich outer core generates a magnetic field. So hopefully from your Key Stage 3 you can sort of recognize a magnetic field sort of coming out of the poles and then moving outwards. Okay, and this helps to deflect these charged particles. And these deflected charged particles, we call these charged particles part of the solar wind. And these charged particles are deflected, and that prevents them causing damage to living things and their DNA on the Earth's surface. So, life on this Earth developed fairly shortly after the crust was solid enough and the atmosphere was thick enough to generate an atmosphere with liquid water. So we think life developed about 3.5 billion years ago. Now, it's quite hard to sort of build up evidence that far back, so a lot of it's been destroyed by tectonic activity. But we think that the atmosphere was very high in toxic gases that we would consider toxic now, so things like NH4 or ammonia, carbon dioxide, and things like methane. Now, if we were put there now, we would find that this was really toxic atmosphere. But this is actually really important for the development of life because things like nitrogen, carbon, and oxygen, and even the hydrogen are really important elements for life to evolve. So it needed to have this sort of toxic soup to develop in. We also find that the Earth's surface would have had high levels of UV radiation, ultraviolet radiation, reaching the surface, which is really toxic, like damaging to life if it's not protected by something like a layer of water. Okay, so this is where this is the sort of environment we think life first evolved, and it's very different to what we see now. So thanks very much, and I look forward to seeing you at our next lesson.